Today I'm gonna present the work that was done actually in Sherbrooke for 2 years and a little bit more since I came to Strasbourg, which deals with trying to make some steps towards an ab initio theory, as we could call it, for high temperature superconductors. And the goal of today is to describe a little bit what's the spirit behind what we are doing, and a little bit of a test case of a study that we could actually achieve in those past 2 years, let's say. So let me first start with a round of acknowledgements. So of course to André-Marie Tremblay and David Sénéchal from Institut Quantique in Sherbrooke University, who welcomed me for the postdoc, and with who we started working on this project in very close collaboration with Christian Howler from the Rutgers University. And let me also acknowledge that there is this work involved actually the work of an intern student, Benjamin Lacasse, in the Sherbrooke University last summer. Also a word about the funds and computational resources that we got during the project. And let me also finally thank the organizers for having me to talk today to everyone around. All right, so this is the outline of the talk. I will start with a brief introduction and motivation about the work. Then I will describe slightly the methodology that we use and in some sense developed a little bit. And then we'll present a test case, like we discuss physics about some type of cuprates, high temperature superconductors, which are called multilayer cuprates. And in the end, I will try to conclude and take quite a little bit of time to discuss what are the current limitations, because I think it's interesting in this kind of presentation to discuss limits, and then also open some perspectives about what's coming in the future. All right. So since we'll talk about superconductors, it's always kind of a start to discuss a map of what is existing at the time. So here is the map of basically the main superconductors that we know with the critical temperature and the y-axis versus the year where they were discovered. There is a few of them that are not there that I removed just for a little bit of clarity. And when, as theoreticians, we see such kind of plot, where of course the TC are measured experimentally, first questions that comes to our mind is, well, can we predict the critical temperature of all these zoo of compounds? Well, to answer this question, as far as BCS superconductors are concerned, this is always almost, I think, done. So there is a very well-established BCS theory, as everyone knows, and this allowed, with quite some intensive work from these people, this allowed the implementation of predictive algorithm based on density functional theory with special exchange correlation functionals, which are quite successful at predicting the critical temperature. So here's an example of the work of Sana and collaborators, published in 2020. And you can compare the black bars, which are experimental measurements, versus the green bars, which are the theoretical estimations. And you can see that it's working pretty well. For high temperature superconductors, and especially cuprates, in which I will be interested in this talk, well, we were quite far from, from these results. And I think that there is probably three main reasons that could explain that. First, there is no well-established theory, or should I say there is too many of them. And so there is nothing that tells us what should I compute or what should I include, say, for instance, in exchange correlation functional to estimate the TC from DFT in a material-specific way. The second element is that we deal with strongly correlated systems, which makes that the treatment of these systems from the theoretical point of view is much harder. And a third point, I think, which should not be neglected when it comes to cuprates, that they have a very strong doping dependence, right? So even if you would know the different compounds that you have to test, you still have to span the whole doping range, and so the whole phase diagram, to be sure that you have basically seen superconductivity, the whole superconducting dome. So this makes our life quite difficult. So to answer this question about high temperature superconductors and trying to get some knowledge about the physics of these systems, a very successful strategy was basically to use simplified models. This has been used since the discovery of these compounds. And the idea is quite simple. Instead of considering the full crystal with all its degrees of freedom, what we do is basically keep only a few well-selected degrees of freedom. For instance, here is represented a 3-band Hubbard model with a few parameters, and then try to basically describe as far as we can the system with these only few degrees of freedom. And this is quite actually successful. Immense progress has been done thanks to effective models. And I think that one work that kind of summarize all this progress as far as superconductivity in cuprates is concerned will be this work by Kowalski and collaborators, so which was done in the group of André-Marie and David in Sherbrooke, where they could identify, if I would summarize, 3 key parameters for superconductivity, which relates to all these experimental works which are cited here in the slide. So these parameters would be the charge transfer gap, the oxygen hole content, and the spin exchange J. So once this is settled, of course, the question remains open is how can we relate these 3 parameters actually to the crystal structure or the crystal parameters of my compounds? So can we really make material-specific predictions of these 3 parameters, for instance? Or can we make material-specific predictions of the superconducting properties themselves? And we thought that, well, there is still some work to do, and I think that a very simple example will be this one. So if I take one plot from this work of Kowalski and collaborators, where we see in y-axis the maximum superconducting order parameter, say that would be basically your density of pairs in the system, versus the super exchange J, the theory tells you quite nicely that you should expect a quite simple correlation. So the higher is the super exchange, the higher is the density of pairs. So you would think the greater is the superconducting properties. We can look at the experimental counterpart of this plot, where you have J, again, so the super exchange interaction on the y-axis versus the critical temperature on the y. So here, take this with a grain of salt, of course, because critical temperature is not superconducting order parameter. The two are not one-to-one in one-to-one correspondence, but say that at this stage, this is what we can compare. And you can see that while there is a bunch of materials that seem to show or motivate this correlation seen in theory, there is actually quite a nice group of them that tells you that this is not so simple, and that some more work has to be done, and some perhaps new methodology would need to be developed so to be able to explain why these few examples would be so far away from the others. So this motivates the idea that we perhaps need some more advanced ab initio method to be able to really carry material-specific predictions. And so maybe at some point to advance a little bit on what critical temperature we can achieve in these materials. All right, so this is basically the goal and the end of the introduction. So what we aim to do in the end is to construct such fancy algorithm that will be fed with just the crystal structures as input, so really a DFT-like approach. And this fancy algorithm should give us not only an estimation of the superconducting properties, but also we think that it should also provide us at the same time, simultaneously, a knowledge of the magnetic spectral properties, also structural properties. And why? Simply because we don't have yet a well-established theory for high-temperature superconductivity. So to be sure that we have the key ingredients in the algorithm, we should not look only at the superconducting properties, because by luck you could get some good estimates, but something could be wrong inside. And so you have to compare all of these other properties with what is known experimentally. So to be sure that what's inside here in the fancy algorithm would be the good ingredients. Okay, so that's basically what we try to develop, to have something that gives us all of these different properties from the same framework, not necessarily from one very calculation, but at least from the same framework we get all of these properties, such that then we can know if what we have developed is will be useful or not. All right. So in the next part, I will basically describe the methodology, so what we have tried to implement so to get to this goal. Okay, I will not go into the very details of it, but just try to give rather the philosophy behind, and then if you have questions, we can discuss this more into details. Okay, so of course the first step in constructing such a method that will give us some material-specific prediction is based on to use a density functional theory. I mean, we have no way around that. So just in short, I think it's nice to remind a little bit of DFT, especially in the DMFT community. So let me just quickly remind the three the main ingredients, let's say. So this is a first principle method, right? So this is what can help us in in overcoming the model's ambiguities, if you could state it like that. It's a ground state technique, right? So DFT gives us an estimation, an approximation of the ground state energy, which in many cases is extremely accurate, right? I mean, even for systems that we would think as correlated, DFT can actually give you some very nice estimate of the ground state properties, even structural properties. However, we have to keep in mind that this DFT uses an auxiliary non-interacting system, which we usually call the Concham systems, which means that if you want to get to the knowledge of excited states, or another way to say it is to get response functions, there we will get a fundamental limitation, right? Because the response function of strongly correlated systems are deeply multi-electronic, and this is a type of physics which is not in the basic density functional theory, which would not be incorporated, because it's not meant to do such type of to compute such type of response functions. So let me sketch that in a very simple example, because I think it's important to understand where does the DFT limitation is, because this tells us what we should actually improve by combining DFT with dynamical mean field theory. So imagine the system of n electron in its ground state. So if box would represent one electron, for instance, you can think of a spin model if you want. And when you do a measurement, experimentally, what you do is basically you perturb the system and you measure its response. So when you do an experiment, what you do is necessarily to measure response functions, right? So RPES, for instance, would be a one electron perturbation. And if your system is weakly correlated, well, you will perturb one electron. For instance, you would create a photoelectron from one of them, when all the others would basically not see anything, right? Because they would be weakly correlated. So this is as if you would basically probe a pure copper, piece of copper or something. In this case, well, DFT could be quite good because you could use the one electron states from the Concham system, and probably you would get some good estimate, let's say. However, if your system is strongly correlated, the fact of perturbing one electron, because of the electron-electron correlations, which are quite strong in the material, you would basically spread, the correlations would spread all around. And so your excited state, where only one electron is perturbed, is actually very multi-electronic, right? So we need to take into account these multi-electronic processes into account, because for the physics of cuprates, and I think high temperature superconductors in general, they are actually key and very important. I mean, superconductivity itself is a multi-electronic process. All right, so to include these multi-electronic processes, basically use a combination of density functional theory and dynamical mean field theory. So this is not new, right? So you'll be very careful about to clarify in the next slide what we think is novel, or let's say specific to our implementation. But this is not a new stuff, right? DMFT was invented in, well, I mean, there is a big review of Antoine Georges, of course, in 1996. So I was minus 1 year old at the time. Then Liechtenstein and collaborators did the first combination of DFT plus DMFT in 1998. So I was 1 year old. And in our case, we used the implementation of Christian Hauler, which is nicely described in this paper of 2010. okay, which basically follows the spirit which I will describe now. So imagine that you have your crystal structure on the left with the copper and oxygen planes. So here I took the example of a cuprate, of course. Then the idea is to say, well, we have this full crystal structure with all its degrees of freedom that we cannot, in which we cannot treat the electronic correlations because it's too complicated. So what we do is we project. So imagine that you, in the same spirit as DMFT on the Hubbard model, you would project all the degrees of freedom which are around this cluster of copper, all right? And you would get basically into an effective impurity problem where you have, in our case, 4 copper, so a 2x2 plaquette impurity. And on each copper here, we will only keep the dx squared minus y squared orbital, which is the one that lies basically at the Fermi level and which form this Zhang-Rice singlet. And integrating out all the rest of the degrees of freedom, he can be cast into an effective electron bath with which the impurity can exchange electrons dynamically. And the only difference with when you apply DMFT on the Hubbard model is that here, basically, we project all the degrees of freedom of the crystal, right? So the electron bath contains all the other degrees of freedom of the system. So not only the other copper dx minus y squared orbital, but all the others, everything that lies there. Okay. So then this effective impurity, we can solve it with impurity solvers. In our case, it will be an exact diagonalization solver. We'll discuss this in the next slide. And if you solve this effective impurity model, then you get this function that we call self-energy, which corrects my one-body propagator by including all the multi-electronic processes into it. And similarly as what you would do in DMFT in the Hubbard model, here you would embed, so put back the self-energy on the, basically, on the copper, so you would embed it into the Concham basis, which will modify the rest of the degrees of freedom because you would need to recompute the charge density of the system, and then you would loop again, do the projection. Your bath will be modified, so you can solve a new impurity problem, get a new self-energy, and loop all around until you converge both the charge density and the self-energy. Okay. So what is special to what we have implemented is that we have implemented in such a way that we can do some charge self-consistent DFT plus cluster dynamical mean field theory, right, with a 2x2 plaquette, so to get the wave, and so to be able to describe the wave superconductivity. To be able to take care actually of superconductivity, we use an exact diagonalization solver developed by David Sénéchal in Sherbrooke. And this allows, let's say, 2 main points. So, of course, to reach the superconducting regime because it works at 0 temperature. And this enables us to have a simultaneous description of the structural, magnetic, superconducting properties, but even structural properties within the framework of Christian-Hauler. And the ED solver also allows us to speed up quite a lot the calculations. And actually, the DMFT part becomes much faster than the DFT part. So DFT becomes the bottleneck. And this is quite important for the study of multilayer cuprates, as I will describe afterwards, because there we deal with quite large crystal structures, up to 100 of atoms. And that's more or less the limit that we can reach at present. Okay. And just for matter of detail, superconductivity is, so we do the charge self-consistency in the normal state, all right? We don't allow superconductivity to appear. And then at fixed charge density, we do a last cluster dynamical mean field theory calculation post-processing to see if superconductivity arises or not. And the idea is to say that superconductivity, for instance, the superconducting gap, is the smallest energy scale in the system, in the calculation. So it's okay to compute it later on as a post-processing at fixed charge density. All right. So this is basically, I think, a nice map of what the methodology is and what it contains. And so now we'd like to discuss an application. of it to the problem of multilayer cuprates. If you have questions, I mean, don't hesitate to stop me or to ask questions about the methods. Otherwise, I can follow. I can continue. So we got interested into multilayer cuprates. One reason is quite simple: is that there are materials which are quite complicated to describe with effective models, and for good reasons. So instead of usually cuprates, we think of them as having one copper-oxygen plane separated by charged reservoir layers. The difference with multilayer cuprates is that you can actually have n, so a certain number of copper-oxygen planes in consecutive, which are then separated by charged reservoir layers. And the superconducting properties of these compounds depends quite a lot on the number of consecutive copper-oxygen planes that are separated by these charged reservoir layers. So you have this plot on the left, which shows this universal trend where you have critical temperature on the y-axis versus the number of consecutive planes on the x-axis, and you can see that the Tc is always maximum for the tri-layer compound, so n equals 3. And this is not understood. This is still an open question. What is the origin of this dome-like dependence? And this is basically what we aimed at answering during this study. And what makes the study of this system quite complicated is that these different planes are not equivalent. So here you can see the labels OP for outer plane and IP10 would be the different types of inner planes. And you will see that these different planes basically are, when we dope the system, we dope only in the charged reservoir layers. And so the different types of planes will not be doped in the same way. And even prior to doping, we'll see that there is some intrinsic differentiation between these different planes. This is something that was not, we believe, properly understood before. And so that's one thing that we contributed, I think, to unveil in this study. Okay, so we'll study two families. I will mostly talk about this NCCOC, which is here shown on the right. So it's made of calcium, copper, oxygen, and chlorine. And we also studied another one based on the mercury. We look at the crystal structure from 1 equal 1 to n equal 5, right? We use a 2x2 cluster impurity, the x1 minus y squared orbital. We set a U of 12 electron volts for all the compounds. So we have only one fixed parameter for all the calculations. And we'll see that with only one fixed parameter, we can actually get a lot of knowledge about the physics of this system. And as far as doping is concerned, we use the virtual crystal approximation to ease a little bit the treatment. All right, so let's start with the undoped system. So here is the NCCOC compound, undoped, right? So there is no doping. This is the stoichiometric compounds. And I first show the charge transfer gap. So this is the density of states as a function of number of layers, as you can see. And you can see that there is a charge transfer gap that basically diminishes from n equal 1 to n equal 2, and then from n equal 2 to n equal 3. And then it saturates from the tri-layer compound. We can compare that directly to experiments. That's quite nice. We have some STM data from two different papers. One is for the NCCOC, so the very same compound. And you can see that there is also a very nice reduction of the charge transfer gap from n equal 1 to n equal 2 of the same order of magnitude. So here it's 500 millielectron volt. In the calculation, it's rather 300 millielectron volt, but it's the very same order of magnitude. And for the n equal 3 compound, we don't have data for NCCOC, unfortunately, but we have them for the bismuth-based superconductors. And you can see that there is indeed a further reduction of this gap as n equal 2 to n equal 3. So this seems to match quite well. Then we can ask, well, why is there this reduction of the charge transfer gap? So we can look at the spectral function resolved in momentum. So this will be basically your spectral function measured in RPES, say if you would look below the Fermi level at 0. And you can see that here I plot for the n equal 1 and n equal 2, there is only a purple spectrum, which is corresponds to the spectrum of the outer plane, right? And you can see that there is basically just a reduction of the charge transfer gap in these outer planes. But as you go to the right, to the tri-layer compound, now we have both outer planes and inner planes. And you can see that the outer plane remains relatively constant with respect to the n=2 compound, but the inner plane has a smaller gap. Right, so this further reduction in going to the two-layer compound to the tri-layer compound is basically due to this presence of inner planes. And here there is no doping whatsoever, so it's really intrinsic to the compound that the inner plane seems to have effectively a little less correlation than what is in the outer planes. Okay, so we can further ask why. I mean, it's as if you had a three-year-old child that would ask you why in repetition. Right? So why is this inner planes having a lower gap? So here is, I believe that we can understand this by looking basically at the DFT band structure. So here is the band structure of the one-layer compound and two-layer compound on the right. These are bulk system, right? If I just say one or two layer compound, it's a number of consecutive planes, but they are really a bulk system. And the only difference that you see between the two is basically this extra conduction band on which there is some dotted points on top, which in the n=2 compound lies quite below the rest of the bunch of spaghetti of the conduction bands. Because this band is isolated, we can perform a Vanier fit just to try to get an intuition about what's the physics of this conduction state. And the Vanier orbital that we see is basically this one. So it's a very spread orbital in the interstitial region between the copper-oxygen planes. And this tells you why it does not exist in the n=1, because this state needs to have at least two consecutive copper-oxygen planes, so to be able to live in between them. Okay, so this is really a state that is basically confined between the copper-oxygen planes. And this can be basically extended to the n=3, 4, 5 compounds for which we have done the calculations. So if I come back just here quickly, here you see one state for the n=2. If I go to n=3, we see two of them, n=4, 3 of them, n=5, 4 of them. And if you look at the M point especially, the distribution of these energies is quite peculiar. There is some very simple relations that relate them, which is very reminiscent of thin films. So I basically use the same methods as thin films to study these states. You can plot their energies as measured in DFT versus their just number and some thickness, estimated thickness of the quantum well. And then you can fit basically this data with a quantum well model very, very easily. So this tells you that basically these conduction states behave as confined states in between the copper-oxygen planes. And these conduction states offer basically extra hybridization for the inner planes more efficiently than for the outer planes. This is similar to a surface type of physics, right? If you have a plane which is at the surface, it sees only only one side of the plane sees the rest of the system. While if you have a plane which is in between, then it has both sides. Basically, it can hybridize to both sides. So this is basically what's happening and what's promoting a little less correlation in the inner planes. Okay, so we have understood quite well, at least from what is intrinsic, let's say, to this system, even before we can dope. And so now we can look at the normal properties. How do they behave when we dope the system? And I think a nice way to see how the doping becomes inhomogeneous is to look at the Fermi surface. So here I plot the Fermi surface of the n=3 compounds on the left, both type of compounds, COC and mercury-based. And we can see again the differentiation between what is here, the outer plane in purple, and in yellow, orange, the inner planes. And you can see very different types of Fermi surfaces because they host very different number of holes. Right? So the inner planes are much less doped than the outer planes. So this is already quite nice, but we can also look at what's happening in the 5-layer compound. And here we really see coexistence of these arcs and also these pockets that we can also, distinguish here already in the tri-layer compound, and an additional, even smaller pocket here, which will correspond to the innermost plane in the system. And of course, these pockets, they are perfectly symmetric with respect to the antiferromagnetic Brillouin zone. Okay, and because this is basically the folding of these pockets is coming from the antiferromagnetic fluctuations. This we can trace back from the physics of spin polarions and so on. Okay, and well, of course, this is beautiful, but it's better if you can compare to experiments. So this is a comparison to experiments. Below, you have a tri-layer compound, bismuth-based superconductors, which was measured in ARPES in this work of Hideta and collaborators, where you nicely see these two arcs of different size. And then you have the 5-layer compound measurements of Quinizada and collaborators from 2020, where you really see this coexistence of two pockets and outer arc. So this, we believe, tells us that we are probably doing the right thing. So this inhomogeneous doping has some very important consequence on the superconducting properties. And that's where we believe we can start to understand this dome shape of the critical temperature that I showed a few slides before. So what I show here is the maximum order parameter. So we do the calculations for several levels of dopings, of total doping. And then we look at what is the maximum order parameter for all these dopings. And we can separate the order parameter in the different layers. And what you see, what is striking here is that for the n=4 and n=5 compounds, you can see that the inner planes are not superconducting. And they are not superconducting because they lack of holes, basically. So the n=3, those are tri-layer compounds, basically are the compounds which probably provide the best compromise between having inner planes, which will be protected from any kind of disorder and so on that would come from doping, but still that would be, let's say, doped enough such that they can really host superconductivity. And this may explain why this critical temperature has a maximum at n=3. All right. So I'll just skip this slide. This was just to illustrate that indeed below a certain doping, superconductivity does not emerge. This is seen experimentally, and this is also seen in our calculations. And I would rather now go to the conclusion, just not to take too much time. So just to quickly remind what has been done in this work, basically we set up a method that is able to simultaneously predict spectral, magnetic, structural, superconducting properties from the same framework, right? And from that, we could provide some interpretation of several trends in multilayer cuprates regarding the normal properties such as charge transfer gap, Fermi surfaces, and so on, and properties which are not obvious to predict in principle, which is this doping homogeneity. And then we can make the link with what are the superconducting properties and how can we understand these trends of superconducting properties in these multilayer cuprates. About the limitations, I think that it's important to state them now. So for now, we still have one fixed parameter in this study, which is this Hubbard-U interaction, which is usually the problem with our type of approaches. But well, this is still something that we have to set by hand. At present, we only have access to the superconducting order parameter to describe superconductivity, so we cannot make claims about critical temperature directly. And the trends that we obtain can be seen as, in some sense, weak, unless here for the inner planes where it's really clear. And we can also only account for one orbital per cluster site. At present, this is a limit of, well, the impurity solver. But it seems that even in this limited, let's say, framework, we can understand quite a lot about these systems. All right, and so about the perspectives, we're working at including the competition with antiferromagnetism, try to implement also the computation of the superfluid stiffness that would come as another proxy to study superconductivity there. Also working a bit on the ab initio determination of U. This will take some time. And many more. We started to study the effect of pressure and so on. So we believe that it's basically the first step in a quite fascinating research program. And I mean, the hope is that the community can also start to embrace this type of methods and such that we can progress, let's say, as a community on these topics. So with that, let me thank you again for your attention. Thanks again to André-Marie, David, and Christian, and Benjamin also for the nice collaboration. And if you have any questions, we'd be happy to answer. Thank you very much.
Thank you very much, Benjamin. I think Olivier is monitoring some of the questions.
Can I enter the game?
Please, Henri. Yeah.
You hear me? Okay.
Yes.
Very interesting work indeed, because we are waiting for this kind of work for long, because the NMR has shown at the beginning that that difference between the inner plane and the outer planes. I have one question which I think you didn't address, which is, do you find what do you find about the pseudo gap in the case where in the layers, which the inner layers in principle, NMR experiments have shown that there you have you are really in the underdoped regime, and see a pseudo gap while the outer layers do not in some of the compounds. I don't know. I think in Bisco. So do you have any indications going that way? Because you are saying that you change the charge transfer or something like the charge transfer gap.
So what you said is in the outer planes, there would be no, you have passed the overdoped regime and
you can be overdoped in the outer planes and be underdoped in the inner planes, which is what you are telling us.
Yeah, so, if we look at
you are telling us that you have less charges in the inner planes than the outer planes.
Yes. Yeah.
So it goes in this direction, which is that the layers are somewhat decoupled, and this is what was observed in NMR.
Yeah, this is what we see also, that the layers are quite decoupled. So I think we have not reached the stage where the outer planes would be not in a superconducting regime anymore, because I didn't push too much.
I don't think you reach that case in the actual materials. In the actual materials, superconductors, and they are superconductors because of the outer plane.
Yeah. So
no, my question is: do you have any possibility to generate to find out the pseudo gap as well?
Yes, I mean, what you see here is basically the pseudo gap in principle, right? That you have arcs forming. So of course there is always a grain of salt taken here because there is periodization involved, but in principle this is a pseudo gap, and we see it also in the spectral function momentum resolved. So in principle we could also discuss the pseudo gap from these calculations. Here it was not the goal, so we did not do let's say a very doping
so my question
fine-tuning of the doping.
My question is rather, is that what would occur for single layers? That is, in some sense, this inner layer, is it really in the same situation as a single layer, in some sense, less doped?
Yeah, well, yes. As far as we can tell, the inner layer seems to behave quite similarly to the outer planes, but less doped. Although there is this small subtlety that the correlation seems to be slightly weaker in these.
This is what puzzles me, because you say that correlations are weaker, but still you would be in the pseudo gap regime because the doping is small, in some sense.
Yeah, I mean, the correlations are, I mean, weaker. I mean, you can see here that the difference between the outer planes and inner planes is a few hundreds of millielectron volts. So it's not a drastic decrease of the correlations. Yes. So
That
it's slightly less correlated, but still enough that you would open a gap and get a pseudo gap at in the unadopted regime. Yeah, as far as I could tell now.
It seems to be in agreement with some of the
Yes.
more experimental facts than you are mentioning so far.
Yeah. Yeah, for the pseudo gap, it was not the goal of the first goal of the study, but yeah, we'd be happy to.
I understand, but this was one of the first evidence in these 3-layer systems from the really very, very early times, from 1992 or 3, I don't know. So it's an old story. Okay, thank you very much. Very nice.
Okay.
Antoine, you want to ask a question?
Yes. Can you show again your Fermi surfaces for the different layers? Thank you. Yes. So I want to make sure I understand that. So what you are saying is that the inner layer has a very low doping level, right? And then it leads to a very small pocket, which seems from the plots to be centered around the nodal point, around pi over 2, pi over 2, correct?
Exactly.
And how does that happen? Is this because of the antiferromagnetism? The calculation is, in fact, in an antiferromagnetic state, or what's going on here?
So that's the funny part. It doesn't have to be in the antiferromagnetic regime, so to have signs of antiferromagnetism. So I think we can see it more clearly here. So if you look at the bottom part of these spectral functions, you can see between gamma and m, the dispersion basically is split it into two small parts, and one is it has a dome shape between gamma and m at roughly at the level of the dashed lines. There is already dome-like.
But so in technical terms, this is all 2x2 clusters, right?
Yeah.
So
but this you can see.
So this depends on the reconstruction, momentum interpolation schemes you're going to use.
Yes, it depends a bit on it, but it's also robust. I mean, we have done a study in another work where we had like 8 side clusters and larger clusters. This is really basically linked to this waterfall type of physics in cuprates. So this basically is the sign of a spin polaron physics. Okay,
so what you are saying is that they are strong, but short range antiferromagnetic coalitions, and that those are enough to reconstruct basically the Fermi surface around producing a pocket around the nodal point. Can you quantify the coalition length? How in the calculations you did, do you have an idea of what the antiferromagnetic coalition length is for those inner layers?
Yeah, that's a hard question to answer, because in the end we only have 2x2 clusters. So to me it would be hard right now to tell what would it be. I think I would probably need some extra computation, let's say, where we would try to include a little bit more length scale, increase a little bit more the length scale.
No, in principle you could do it from 2x2 clusters if you were courageous enough or bold enough to actually calculate the full vertex and then go to the susceptibilities, right? Even with 2x2. You could say something, but that does require rather demanding extra calculation.
Right. I mean, it's on the list going towards 2-particle response functions. At present, with the ED solver, it's not yet possible. We can have some parts of it, but it's on the list. So there we could probably say something later on. But as far as this work is concerned, I would not make any claim about that. Yeah, sorry. But
okay, thank you.
Okay, maybe one last question, quick question from Hangui Chen.
Oh, hi. Can you hear me?
Hello.
Yes.
Yes. I just want to make sure I understand your the so-called cluster DMFT calculation correctly. So for each copper O2 plane, you're using this 2x2 cluster to for example, to study the D wave superconductivity, right?
Yes.
But then you also have multi-layer system, right? So do you take into account the interlayer correlations as well?
No. So at present, each plane will be, for instance, linked to one cluster impurity.
Yes.
And
then for each layer, you do it separately, right?
Yes, exactly. Yeah. So the layers see each other at the DFT level and via the hybridization function in some sense, but not directly into the impurity problem.
Yes. Okay, I got it.
So
but
they
my
see
question
themselves
is
as the mean field. Yeah.
Yes, but my question is that do you think it is justified to ignore that interlayer correlations?
So we did some check where superconductivity, we looked for the proximity effect for superconductivity. So but it was the same that the layers would see each other as mean field. So right now it's too expensive to do
yes, I understand that, but
ellipsoid cluster. So we don't think it would be so sizable because the thing is, your hopping terms between the planes would be quite small compared to the others, and in such case, usually the surf energy would make it worse. Because it would promote rather hoppings into the inner planes rather than between the planes.
okay.
I mean, to describe superconductivity in a very, let's say, a fine grid terms, perhaps you would need to include these interlayer correlations. But I think that for the, let's say, at least big picture, we don't think that it's the main limitation, I would say.
Okay. Okay, thank you. I just want to give us a quick comment from, let's say, other communities. For example, we study, like, the nickelate superconductors, and you also mentioned that in your talk. So we have this bilayer nickelate, which becomes superconducting under high pressure. And it turns out that you must have two nickel layers in order to make it superconducting. If just one nickel layer, it is not superconducting. So it turns out that this interlayer correlations seems to be important. And from your comment, it seems that in cuprates, this is not the case. In cuprates, I think that this interlayer correlations between the two copper O2 planes probably plays less important roles for superconductivity. I guess that is your comment, right?
Yeah, at least here the trends in terms of TC versus number of copper oxygen layers seems not to be necessarily very linked with the interlayer coupling, rather than when you have two layers, they are slightly less correlated. So if this can help, probably with yeah, I don't think that the interlayer coupling would necessarily be the main ingredient. Here it's rather that these planes are doped very inhomogeneously, so this is what probably in the first place shape the superconducting properties of these systems.
Okay, got it. Okay, yeah, thank you very much.
But thank you very much for answering the question. Yeah.